So my talk today is kind of going to focus on a variety of different things. I want to first start with just acknowledging the work of my collaborators, and this is not a complete list. I would say that, so Guy Alderker is my graduate student who is here, who gave a poster presentation yesterday, is responsible for some of the excellent work that I'm going to present, but also two of my former postdocs, Claudio Torres and Catherine Salem-Ruiz, who is now in Luxembourg, but she was a part of an IPAM program last time, so part of this work was generated here, as well as Dmitry Golovati in Akron, and my new collaborator from mechanical engineering at George Mason. So my background has been in modeling of microstructure, so very similar to what Katerina was talking about, and this has been occupying my brain for like 10 years, and somehow in pandemic things shifted, and I discovered the newfound interest to risky problems. So what you will hear about some of the preliminary results in one of the projects that we have that has to do with modeling additive manufacturing. And that's going to be the majority of the things that I will kind of frame the theory that we're developing in. But I also have a couple of other projects that kind of fall within the framework of this workshop, and specifically we are working very closely with a group in thermodynamics to understand the phase diagrams and how to compute and automate the procedure for phase diagrams. And there is a lot of developments right now in terms of uncertainty quantification. And I'm happy to talk to anybody who wants to discuss that later on. I also have a project right now have to do with learning non-local interactions in the orbital free DFT, and that's a separate work that we're doing at Mason. But the majority of the stuff I'm going to be focusing on lies kind of in the realm of microstructure and additive manufacturing, which I think is a fascinating application, and there's a lot of need for mathematical development. So kind of roughly what I like doing and what my group has always been focusing on is understanding how to automate things, how to optimize, how to find a relationship that can help speed up the computations and also guide the experimental design. So in most of the things that I have been working with, we have to perform some sort of data-driven modeling across the scales, and I like to go from the very bottom to the top, or at least to in some subset that doesn't belong to one scale. So usually there's processing parameters that we try to optimize, or microstructure parameters which are mesoscale, and then we go all the way to the macro scale when we talk about mechanical response. And we want to understand the mechanism. So this is really what's driving some of the work that we're doing. And at the end, it's an optimization problem. And a lot of the things that I'm talking about falls in the realm of something that people call machine learning nowadays, but it's also just optimization and fitting sometimes, and it's just data analysis. So the methods that I'm building, so this is kind of the toolbox that we're trying to discover as we go and see what needs arise, has to do with feature extraction, reduced order modeling, learning process property maps, and this could be a manifold learning type of work, and also identifying dynamics and parameter estimation. So there's a variety of things, but I hope that I will, at the end of the talk, give you a glimpse of how they all fit in some of these applications. So what drove me to this new project in terms of modeling 3D printing or additive manufacturing is just the sheer complexity, and also the fact that there are so many interesting questions that have to do with how to really make this process work the way we want it to work, and how we want to predict the microstructure, how we want to predict the performance of the material, and can we control it. We're using it more and more every day. Engineering field is booming. So can we put some mathematical intuition? Can we put some methods in place? So this is the method that this is the framework, the integrated framework that we're using. So I have collaborators in Luxembourg. They're performing the large-scale simulations of the power fusion, and then basically what we're getting out of these simulations are parameters that have to do with powder spreading, scan patterns, laser parameters, and chamber gas. All of these processing parameters that are essential in controlling the results of the process. But then, there needs to be the defect analysis. So there are a lot of defects in this process that get generated, and there's a variety of different terminologies. There's gas pores, there are keyholes, there are lack of fusion defects, and they result as a complex modeling artifact, but also in reality that you see this in experiments as well. And then after you have these defect information, we want to look at what happens to the fatigue life. So we chose fatigue, but you can do similar things with mechanical response in terms of elastic and plastic deformation. So that's kind of roughly what we're looking at, and there are many people involved in this effort, but this group of Bernard Petters in Luxembourg, they're developing the code that incorporates these equations. So basically you have energy conservation with boundary conditions. There is some sort of rate of melting that you assume. So all of these have a lot of different modeling parameters. And I'm stressing that the fact that there are a lot of modeling parameters is something that I want to focus on, right? So we want to actually reduce that number. And then we have, momentum conservation, rate of melting, and such. And then there is a lot of different things that you can do. You can modify the laser speed, the bed height, all of these parameters in terms of in which direction you scan the sample, how you put it on top. So all of these technicalities. But you produce different results, right? And then you have to do the microstructure analysis of the sample. And so this work is actually the KMC type of simulation that they're doing, which you can see is kind of roughly, it's very uneven, and it's very different from the pictures that Katerina has showed, because there's a lot that's going on in this process. And there's a very quick solidification, and then there's another pass. So the microstructure is really tough. It's really not easy to even understand what it looks like. And so what we started with, NIST, National Institute of Standards and Technology, has a set of benchmarks. So they actually calibrated their experiments, and they carefully curated the set of data for the specific purpose of additive manufacturing modeling. So we took a couple of samples, we looked at them, and they provide this microstructure. So these are experimental samples. And you can guess that this is going to be the case, but obviously, depending on how you cut and which part of the sample you look at, you will have a very different structure, and of course, it will manifest in different probabilities of you getting a fracture or some sort of different mechanical behavior as a result. So there is a lot on their side that people have done to understand. To work with these specific samples with specific examples, and people are competing which model works best to represent these experimental results. But for us, the first thing that we were trying to do is to understand, first of all, can we do something fast, right? And fast sometimes doesn't mean good, but one very long-standing problem in this field is to trace the boundaries of these grains. And so, our collaborator, Katerina Barmak, used to use graduate students who would just trace it by hand. And of course, nowadays it's an imaging task, so it should be done by a computer. So we should not subject anyone to this labor if we can afford it. So indeed, so there are tools, and so this particular one is the ML algorithm. It's using Sobel filter, and it's doing a pretty good job. It's tracing those boundaries, and the images are kind of they're nasty. They're really not so clean, and you can see defects inside. But you can actually get the boundaries, and it can tell you the size of the grains, and all of these characteristics. So it's nice that you don't have to really spend hours tracing it by hand. Yeah.
But did you try to check different statistical metrics? Because okay.
That's next. Yeah, so absolutely. So this is basically what we need to do always, is to look at the statistical distributions, and there are a variety of different measures. So, the software actually does calculate the circularity, the roundness. There's also, what we need to know is the relative areas and dihedral angles and all of that. Whether we have done an extensive analysis, no. But what we have seen so far looks reasonable. I do feel that these methods, although they're fast, they need a little bit of tweaking. The way this model works, I don't know if any of you use this particular software, but it asks you to trace some boundaries by hand, and then it's learning as it goes. So you can see, like, if it needs more input, you would trace more boundaries. So there's a little bit of labor-intensive part, but it's really fast. So in my experience, I traced maybe, 10 of them, and it did a pretty good job. But it could depend also on the image. So it is kind of one very quick machine learning task that we were able to kind of bypass and to use the technology that's available. But then, this is really not telling you much. What we need to understand in this sort of application is how to correlate the processing parameters with some statistics, with some mesoscale characteristics, and with the mechanical response. So this is the image that I'm showing every time I'm giving a talk about microstructure, because there are all of these parameters: the number of sides of the grain, the area, dihedral angles, orientations, and all of these will potentially play a role in the additive manufacturing as well. One particular characteristic that we discovered unrelated to additive manufacturing is the microstructure disorder characteristic. And so it's a very easy concept to grasp. It's just the information entropy type of concept. But what you can do with it is basically look at any variable, any random variable, be it number of sides or areas or any roundness characteristic that you want to impose on a grain, and measure it, right? So I wanted to draw your attention to this because we found some interesting results when we started changing this Shannon entropy and introduced the Rene entropy, which has this parameter beta, which is, basically in the limit gives you the Shannon entropy, but it doesn't have to be 1. And when we correlated the results with simulations using this distance between microstructures. So we're basically computing this Jensen divergence. And the work that we have done, we focused on grain area and the number of sides, but you can use other variables, you can use other random characterizations. So if we just look at this so this was done with DEM, discrete element method. So what we tried to do is just create these samples, which were randomly distributed with a certain with a certain entropy parameter, right? And then we looked at the corresponding strain stress relationship. And what we found is that it's actually very much correlated. So the darker curves have smaller Shannon entropy. So the top one will be the perfect hexagonal lattice. And then when we distort it and we introduce more disorder, then the curves go down. And this was pretty systematic and pretty clear from all of the runs that we tried. So the other thing that we did is we looked at the yield stress. And so there was actually less clear what's going on, because we saw, like, what we wanted to see is some sort of a clear correlation. So if we change the entropy, then the response changes accordingly, some sort of correlated behavior. And it was better correlated for beta equal to 1, and then for the size-based statistic. But when we looked at the sizes of the grains, then somehow beta equal to 1 gave us this big mess. But when we changed the parameter to 2.5, it allowed us to see those clusters better and to see the correlation better. But this is just an empirical evidence, right? So this is not really a theory that can explain, but what it does bring us to is the realization that there could be a lot of different characterizations of the microstructure. And how do we pick one? How do we actually make sense of what's going on? And can we build a theory for it? So again, going back to to these images, which were kind of all fuzzy, and I showed you how we kind of try to understand what's going on with the images. We also computed some of the parameters in terms of roundness, circularity for different legs of that construction that they had in the benchmark. But it's giving us more open questions. It's giving questions about which microstructure properties best correlate with residual stresses, entropies. How does the melt pool play a role in this? Because there is a melt pool characteristics that we have not taken into account. How sensitive are these entropy calculations to the quality of the segmentation, and so on and so forth. So it's definitely a task that you can try and put somebody to measure all of these things, but there must be, again, some way to bypass that manual labor, right? Like there should be some way to automate the process, and that's what is driving our research. So again, an additional aspect to this is that the defects play a role, right? So the defects, depending on where they are, so there are the surface defects versus internal defects, the corresponding stress and fatigue life are affected. So if you have more defects at the surface of the sample, then you see, these black, the blue dots here comparing to the red dots in the internal. And there's a lot of experimental literature on this. So this is not something that we have done, but we have looked up a variety of different papers. And what we have tried to do naively is just to put these defects in the DEM code inside the sample and then move it closer to the boundary, closer to the surface. And we actually have calculations that show that it does affect the corresponding fatigue life. So again, what does it say? There are so many entangled characteristics, right? So how big the defects are, what is the geometry, what is the melt pool, how close they are to the surface. So all of these things combined make a higher dimensional task for us to work with. So what we realized is that it's basically a minimization problem where we have to have some sort of relationship, right? So if we want to minimize defects, that would be this F, the proportion of these, the fraction of defects in a microstructure. We need to also take into consideration the corresponding microstructure characteristics we want to optimize. So we want to minimize some collection of things, right? It's a multi-criterion optimization where we want to achieve the certain elastic and plastic response as well as some characteristics of the grains. And there are so many knobs to pull, right? So this problem actually has, you can focus more on defects, or you can focus more on the microstructure optimization, and then how exactly to go about optimizing this distance between the microstructures is even harder to tackle. So we need to learn some sort of you have to learn the surface if you want, or if you want to somehow a closed form representation of the problem to make it easier to solve. How possible is this? So we're making progress. I'll tell you about some of the methods that we're developing that I think will be fundamentally useful here. So one work that we found that was very relevant is the work by Bakarji et al., just published recently. What they're doing is they're using machine learning in a very unusual way. They're learning the dimensional groups, or so I would rather say non-dimensional groups. So Buckingham pi theorem is this dimensional reduction result that everybody teaches maybe in undergraduate applied math class. And usually if it's a small problem, you can do it by hand. If it's a problem with multiple parameters, you can still form a matrix with your dimensional, with units attached and still do the reduction. What they're doing, they're using neural net to learn this, but as a kind of the driving engine for this is the so-called Cindy method, which is the inferring dynamics from data. So this is the method that was originally developed by Brunton and Cutts in 2016 for learning the dynamics of an ODE. So the way it works is basically you have an ODE system and you're considering kind of a linearized model where you feed a dictionary of functions. And this dictionary is something that the user prescribes, so you have to know something about your functions to begin with, but then you're basically learning these coefficients, right? So it's a method that is very simple, and at the end, it comes down to minimizing this problem. So you have this minimizing the residual, and then you have the penalty parameter. So that penalty parameter is the one that preserves the sparsity. So you want as few of these functions to be in the solution as possible. So you want to preserve the sparse characterization. So that's what this term is doing. And there are a variety of different techniques that people have built on top of this idea. But one of them, which basically I just mentioned, was this recent work that they have done to build the BuckyNet. So it's a Buckingham Pi with this machine learning component to it. And it's doing exactly the same thing. Basically, it's building a library, but it's based on these unit measurements, right? So instead of this library of functions that in ODE you would learn to fit the dynamics, here you're fitting your non-dimensional groups. And what you're trying to do is you're trying to replace the input-output map that you're trying to discover to a mapping between these non-dimensional groups. So it seems to be a nice idea. So that's what we're aiming to utilize. The challenge is still that these groups are non-unique, right? So as you know, you sometimes have to use judgment to pick the right group. So there is some work that people have done actually in this community, publishing what happens when you have all of these groups, how do you pick between them? And then you have to use some judgment. So it's still a multidimensional problem. It's still massive in terms of its in terms of what is needed from a computational standpoint. So what we wanted to do is go a little bit further and understand how to reduce the complexity. Even after we have all of these non-dimensional groups, and if we have a lot of samples, a lot of measurements, we're talking about changing one parameter at a time and doing an experiment again. So it becomes a 2 to the n just in terms of the sample space. But then we also have the parameter space, which if you include everything that I talked about before, it's really massive. So we're going back to the basics and trying to understand, in general, in statistics, you would use like a PCA or SVD to find the dominant directions. And this method, of course, can be used directly, because if you look at their chart, they are using SVD to come up with these modes at the end. But what if we cannot do the SVD? So sometimes the matrix is so large that you just cannot pull it off. So what we needed to do is think about a way to decompose this process and somehow divide and conquer. Use a strategy to reduce the dimensionality. And so this slide is obviously not a surprise to anyone. So this is just a regular SVD decomposition. So you have your unitary matrices, U and V, and you have the diagonal sigma. And then you can, of course, truncate it if you know that the profile of your singular values is decaying. Then you can cut it at a certain point, so you can speed it up. But one of the biggest challenges, and then the one that's preventing us from just directly using SVD, or at least it's presenting a problem, is that when you're doing an SVD, you're projecting on these SVD directions, on the principal components, which don't mean anything. They actually are not physical, right? They mean something for the PCA or the SVD, but they're not your original physical parameters. And so we're going away from really looking at the data, and we're looking at these XY coordinate space, which is not interpretable. And people have thought about this. So you see, like for instance, in this case, it's kind of nicely oriented, but this picture shows that it's really not clear how it's related to the x and y coordinate. It doesn't have to be related. So there is this paper that came out in 2009 that is very interesting, and it generated a lot of activity after that, which is the CUR decomposition. So what CUR is basically, it's a process of selecting columns to get an approximation to the SVD. So you're getting something not exactly equal to the SVD decomposition, but your matrix approximation of your SVD can be made arbitrarily close to your SVD by doing this procedure. Now, of course, so this method we can use, and that's great. So we knew that we can incorporate some of this interpretability, but it still doesn't solve the problem of dimensionality. So what we have done is basically coupled it to the concept of centroidal Voronoi tessellation. And centroidal Voronoi tessellation, if you're familiar with this, is a very powerful way to tessellate a domain, decompose it into cells and find the representative features in the data. And in this case, it's really the distance that we will be talking about is the distance to the subspace. And so this concept is very flexible and generalizable to a variety of different contexts. But here, basically what we're doing, we're picking the distance, which is the projection on the subspace distance, right? And then the objective becomes basically to minimize this function. And so Guy talked about it in his poster, but the solution to this problem, we can show that the energy associated to each step of the procedure that is being taken with this D method, which is a variant of CUR, is basically reducing the error at every step, and you're getting that approximation to the SVD. But what you're gaining as a result is that you have split your problem into subproblems. Each problem is small or relatively small. You can tackle it with the usual DEAM algorithm very quickly, and then you don't have a problem that you faced before. And complexity-wise, it's doing pretty well. So basically, if you just take the non-parallelized version versus the parallelized version, you're talking about the comparison between rho cubed, where rho is the rank, the target rank of the matrix, comparing to LM times D squared, where D is the dimension of the subspace. So in this case, we're assuming the subspaces are same dimension. But roughly speaking, it's the same order. So you're not really doing more, and you're gaining this parallelizability, which is a very powerful thing. So as a result, we want to go further and apply this methodology to the problem and to our data set. And what we are comfortable with saying is that in the experiments that we have run, the error, the reconstruction error, is actually tracing very well the non-parallelized version. So your error, if you increase the number of domains or subdomains, does not deviate far from the sequential code. So the code that is kind of the state of the art in this in this area right now, this DEIM, which is actually based also on the same SINDI principles, and you can look up the paper. It's very similar to the terminology I described. And the bottom curve here, the black one, is the exact calculation of the SVD. So you're not losing in terms of accuracy. What you're gaining is flexibility in terms of splitting your domain. But so what's the point of this is once we have enough data, we should be able to do this type of analysis. So far, this is what is being done in the literature in this area. People are looking at two-dimensional plots, right? So they're looking at velocity of your laser and the laser power, and they're trying to understand where what kind of defects arise in each domain. What we'd like to do, and we don't have the data yet, so the data is being generated as we speak. So hopefully, next time I give a talk about it, we'll be able to reconstruct this property defect life map. Again, this one is a 3D image, but we expect it to be a potentially higher dimensional object, but we can learn the shape of that using the techniques that I just described. And so this is kind of the overall schematic, right? So we have controllable parameters, and we're going through this mechanistic modeling stage to come up with dimensionless groups through our machine learning engine, and then get the PDL map as a result. The question is, what happens to microstructure? And that is a non-trivial question. And as you have seen, so Katerina gave a talk about the different developments and how to model microstructure evolution, even in the context of just this thin film with no additional layers. I'll give you a couple of things that basically can help to understand it, but I will not give you the solution to this problem. So this is the same kind of energetic formulation that you have seen, and the curvature-driven model can be postulated like this. What we do have at this point is we have a variety of different models, which are kind of PDE-type models that Katerina talked about, but we also have simulations. So one type of simulation is based on this straight line approximation, very simple vertex code. So you're basically tracing the motion of the triple junctions, and the boundaries are straight lines. And it amounts to basically the triple junction dynamic equation. It's similar to a triple junction drag. If you're familiar with that concept, it's basically saying that triple junctions are playing the most important role in the process. So we actually have done a lot of work to prove that this particular implementation of the vertex code is stable. So we have stability analysis, kind of like a CFL condition type of result. And still, if you look at the, if you look at what happens to the results, they fall not exactly on top of the on the experimental prediction. And what we saw is that you can change where this curve is, comparing to if you change these mobilities of the triple junctions. And so that motivated us to look into the development of this coupled model, which couples boundaries and triple junctions together. And then you have kind of flexibility to choose the ratio between the two mobilities of the boundaries versus triple junctions. And so this was kind of the Lagrange interpolation type of idea that Claudio Torres and his students have developed recently. And so you can basically implement these codes, and they can actually run on a very large, you can run large-scale simulations with a lot of grains. What you see is that there is an effect of this ratio, as I said, right? So this ratio kappa is the mobility of the triple junction versus the boundary. So if you have 1, then they're equal. But if you have kappa equal to 1,000, then let's see if I have it somewhere here. I did not. Yeah, so basically that would mean the triple junction drag. So right here. All right, so this lambda dominates comparing to the grain boundary. And you can change the shape of these distributions, and you can match it with the predictions of the experiment. But all of this is to say that there are a lot of things that you can modify, but it still doesn't give the full description of the process. So there are mesoscale theories that have been developed, so I will not go over this because Katerina already talked about some of them. So Mullins von Neumann, the McPherson-Strolowitz, and so on. And so this is kind of roughly the hierarchy of mesoscale models. So this is the model that Katerina is extending right now, and including many more parameters than originally stated in this form. We also developed the model that basically treats all the misorientations as particles that are colliding. It's like a gas dynamics model, which resulted in a Boltzmann equation. So in this case, we actually, all of these collision terms do describe the specific reconfigurations that take place during the grain growth. And it's 2D, but it does handle energies that could be non-smooth, for instance. So there are a lot of integrals on the right-hand side of this equation. And we also had this random walk model, kind of similar also to the stochastic process description that Katerina talked about. So this was another attempt to try and model the same thing. But there are still questions. So one of them is, of course, generalization to 3D, which is difficult, but I think doable in some, especially in this case. But also the formal derivation of the continuous limit. So how exactly these models are interconnected. That's still a very interesting question, whether or not, for instance, we can show that the equilibrium for these models match in a certain situation. But the question to me has been for a while, how do we actually go and model something like additive manufacturing? Because that's really much harder to do at this scale. So one idea, and I have not tried this, but there's a lot of literature, and some people have looked into data-driven dynamics identification. I don't think anybody tried to actually fit this particular problem, so that could be an open question. I'm happy to collaborate with whoever is interested in that. And I'll just mention, I did talk about Cindy specifically, but there are physics-informed neural networks that have been tried in this context, as well as dynamic mode decomposition. So the question would be, if we use a sophisticated machine learning technology like that, can we actually get something similar to what we have derived from the first principles? And that would be an interesting task. One thing we know how to do, and we want to use it in this more complicated context, is we know how to add nucleation. So this is the code that we have available. So this is a GPU parallelized code that incorporates stored energy, and that allows us to nucleate grains of specific misorientations. So this is the mechanism that it seems to be actually quite easy and not so sophisticated comparing to the previous descriptions that we had. We did a lot of work with this particular code, so we actually have the code, and I think it's handling like 1 million grains right now. So we have done development of stability analysis. For instance, we for the stored energy, we need to know how to write down the total energy, and based on this, we can say how to pick so for which conditions will we have steady states and the bifurcation change. So this informs the selection of the parameters for this code, and we also know what would be the corresponding steady state. So we tested the code, and we actually derived analytically that if in the absence of the stored energy, this will be 2 pi over 3. If the energy is constant, the stored energy constant, but if there is a stored energy that is, for instance, bigger on one side, then your stable configuration will no longer be 2 pi over 3. And you can actually show this. It kind of looks weird, and it's maybe we're used to having hearing type conditions at the triple junctions, but it will not be that way if you have some sort of stored energy. This is a little bit more details about how to nucleate. So we basically look at the middle of the triangle, and then we remove we nucleate a grain if a certain condition holds. So that's based on the stability principles that we defined, and we have the critical radius of the grain derived for which we can expect nucleation. And so here again, so this is just a picture showing that if you exceed a certain critical radius, then you definitely nucleate. In this regime, it grows, the energy will grow, but so the grains will grow, but the total energy will decrease, and then you do not have a growth in the red area. And the only thing I would just say on top of that, it seems like a Monte Carlo procedure for generating these nucleated grains seems to work well. And it's kind of a roughly Metropolis Hastings type of criteria here. We did employ this polling system for boundary flipping. So the boundaries kind of voted which boundary to flip, which gave a little bit of randomness. But you know, the experimental results, the numerical results seem to indicate that it's doing what it's supposed to be doing. So if you give 0 stored energy to all the grains but 1 grain, then it will grow. And we tried to distribute the stored energy in different forms and did the nucleation at a certain point and look at the statistics. So similar to our previous results, we can see deviations. I mean, the general shape stays the same, but you can actually modify these distributions if you pick this nucleation regime in a certain way. So for this piece, I just wanted to say, so we talked about a lot of different things, but ultimately we want to connect them, right? And so these mesoscale models right now are not yet at the maturity level to be useful in terms of the in terms of modeling additive manufacturing processes, but some of the characteristics that we have are actually showing promise in terms of understanding the relationship between the microstructure and the corresponding fatigue life or elastic response of the materials. We do have these reduction tools, the dimension reduction tools, which comparing to what is done in the literature can promise to tackle a huge data set that would not be possible otherwise. So we feel that this is a really nice way to proceed with some of these approaches that I described. And these GPU codes, although they cannot have the full physical complexity of the additive manufacturing processes, they can shed light on what can be the source of some of these distribution differences and statistical features that emerge. But overall, it seems like this leads to a lot of questions. And I want to just say that we have tried different approaches with machine learning that failed. So whenever we use it, we need to use it with care. But there are promising directions that can help automate image segmentation and tracing of the boundaries for sure, dimension reduction, and possibly inference of the dynamics. I say possibly because some of these things are extremely sensitive, and when a lot of parameters are involved, there are multiple minima, and so this minimization problem is not so easy to solve. So there's a lot of work right now that is going, and I'm doing some work with other projects as well, trying to understand how to make it more robust, how to actually get these models to infer the dynamics properly. But there is a big challenge of experimental data. So if anybody has data related to this, I'm happy to talk later on. And I think I'm finishing a bit early, but that's all. Yeah.